Hello everyone, my name is Daniel Nguyen, and today's material on the semiconductor fabrication process is brought to you by work done in the Scan Lab at the University of Florida under the supervision of Aslam Khan, Cheng Shi, and Dr. Naveed Asadi. The content of this video will be centered around semiconductors and their fabrication processes, and is outlined by the following topic titles: Introduction to Semiconductors, Semiconductor Supply and Value Chain, Semiconductor Fabrication Overview, fabrication steps within the semiconductor fabrication, and more specifically wafer production, photolithography, oxidation, etching, deposition, and CMP, inspection and testing, and then finishing off with interposer fabrication, the glossary, and the references. Today I'm discussing semiconductors, which are materials with an electrical conductivity level that is between that of insulators and conductors. This conductivity can be controlled, making semiconductors highly valuable for various electronic applications. Semiconductors are categorized into two types: intrinsic and extrinsic. Intrinsic semiconductors are pure forms of semiconductor materials without any additional impurities, examples being silicon and germanium. Extrinsic semiconductors are created by intentionally introducing impurities into the intrinsic semiconductor. This process modifies the conductivity of the material. There are two types of extrinsic semiconductors: N-type, which has an excess of electrons, and P-type, which has an excess of holes, which is minus electrons. The accompanying graph on the right compares the electronic conductivity of insulators, semiconductors, and metals. Insulators such as glass and pure diamond have a very low conductivity, while metals such as silver and copper exhibit high conductivity. Semiconductors, including silicon and germanium, show intermediate conductivity levels. The ability to control conductivity of semiconductors by adding impurities is fundamental to their use in electronic devices. It allows for the creation of components that can switch and amplify electronic signals, making them essential for the function of circuits. Exploring the semiconductor supply chain, we'll be focusing on its two main parts, the front end and the back end. The front end is where the foundation of the semiconductor is built. It starts with the wafer stock, which are pure silicon discs, the material that semiconductors are made of. And in the fab stage, standing for fabrication, these silicon wafers are then processed using techniques that create intricate circuits on their surface. This is where a semiconductor begins to take shape, and is a crucial step because of the precision and quality of fabrication determining the performance of the final product. After the wafers are processed, they go through the sort step, where individual chips are tested for electrical functionality. This is important because only the chips that pass this test can be used in electronic devices. The back end is about getting these chips ready to be used in products. The chips that pass testing are then sent to the die bank for storage. When they're needed, they go to assembly and then are later packaged to protect them and prepare them for integration to electronic devices. After assembly, the chips are tested again in the testing phase to make sure they meet necessary standards. Finally, the finished chips are sent to the distribution center, from where they are then shipped to be used in various electronic devices. Knowing about semiconductor fabrication is important because it's at the heart of the creating chips that power our technology. The front end, especially in the fab stage, is where the most critical and complex work is done. Understanding this process helps us understand and appreciate the technology we use and the intricate processes behind it. In summary, the semiconductor supply chain is a series of steps that take silicon from a pure wafer to a functional chip in our electronic devices. Front end is where the chips are created and tested, and the back end is where they are assembled and tested and then distributed. Combined, they make the steps to power the electronics used in our world. Moving on from the supply chain of semiconductors and into the value chain of semiconductors, the semiconductor industry involves a series of steps, from designing to manufacturing to assembly, and multiple different companies play various roles in this process. Firstly, we have integrated device manufacturers, or IDMs. These companies handle every step of the process from design to manufacturing. They have their own fabrication facilities to produce chips. And some of these examples of IDMs are Intel, Samsung, and Texas Instruments. Next, we have foundries. Foundries are companies that manufacture chips designed by other companies. They don't design the chips themselves. They only focus on the manufacturing. TSMC, Global Foundries, and UMC are some of the most well-known foundries. After that, there are fabless companies. These companies design semiconductors but don't have the facilities to manufacture them themselves. They rely on foundries to produce their designs. Qualcomm, Nvidia, and Broadcom are examples of fabless companies. Lastly, we have outsourced semiconductor assembly and test companies, also known as OSATs. After chips are manufactured, they need to be packaged and tested before they can be sold and used in products. OSAT companies specialize in this end of business, and some examples that are key players in the sector are ASE Technology Holding, Amcor Technology, and JCET. Understanding the roles these companies play is important because it highlights the complexity and collaboration required to produce the semiconductors that are used right now in our electronic devices. Each company works in a critical part of the semiconductor value chain, ensuring that from concept to final product, the process is seamless and efficient. Moving forward to the semiconductor fabrication overview. The main steps covered in this presentation for semiconductor fabrication will be wafer production, oxidation, deposition, photolithography, etching, and chemical mechanical planarization, also known as CMP. The first step discussed in the semiconductor fabrication process will be wafer production, a fundamental part of creating semiconductors. Silicon wafers are the base material for semiconductor manufacturing. They are thin discs made from high purity silicon, which is necessary for the intricate circuitry of semiconductor devices. The quality and shape of these wafers are crucial. They must be made from pure silicon to ensure the electrical properties are consistent. Also, the wafers are crafted to be perfectly round and smooth to allow for precise circuit patterns to be built on them. To produce these wafers, specialized equipment is used. The first equipment listed on this slide on the left is the crystal puller. A crystal puller is used to create a large single crystal silicon structure called ingots. These ingots are then sliced into thin discs by a wafer slicer, which is the second image. After slicing, the wafers are not yet smooth enough. They go through a polishing lathe, which is the equipment on the third image, which polishes them until they have a mirror-like finish. Understanding wafer production is important because the quality of silicon wafers directly affects the performance of the final semiconductor products. This is why such precise equipment and processes are used in their production. Next step in the semiconductor fabrication process is the oxidation process. Oxidation can be done in two ways, wet or dry. Both methods are used to create a protective oxide layer on the surface of silicon wafers. This protective layer is made up of silicon dioxide, or SiO2, and is formed through a process called thermal oxidation. This involves exposing the silicon wafer to oxygen at high temperatures. The oxide layer is important because it acts as an insulator. In semiconductor devices, it can protect the silicon, prevent unwanted electrical currents, and also help define the regions of a silicon chip that will be doped with impurities to alter its electrical properties. To create this oxide layer, specific equipment will be used. A horizontal diffusion furnace is one type of equipment where wafers are heated in the presence of gases to form the oxide layer. Another piece of equipment used is the RTP system, which stands for Rapid Thermal Processing. This system heats the wafers quickly to form the oxide layer. Understanding oxidation is crucial because it is a fundamental step in ensuring the functionality and reliability of semiconductor devices. Moreover, the next step in the semiconductor manufacturing fabrication process is photolithography. This is a process used to print microscopic designs on a silicon wafer, which will later become the complex circuits of a chip. The process has several key steps: coating, exposure, and development. First, the wafer is coated with a substance called a photoresist. There are two types of photoresist: positive, which becomes soluble when exposed to light, and negative, which becomes insoluble. After coating, the wafer is exposed to light through a mask that has the circuit pattern. The light causes a chemical change in the photoresist, and in the developmental stage, the wafer is washed, and the areas of the photoresist that were exposed to the light are removed in case of positive photoresist, or the unexposed areas are removed in the case of negative photoresist. Miniaturization is a significant aspect of photolithography. It allows for the creation of very small and complex patterns necessary for modern electronics. The specialized equipment used in photolithography are an ASML stepper, which is a machine that precisely controls the light exposure through the mask onto the wafer. Along with that, a spin coater can be used, which are typically used to evenly spread the photoresist across the wafer. Photolithography is essential in the fabrication process of semiconductors as it enables the production of tiny precise circuits that make up the computing power of the electronic devices. The next step in the semiconductor fabrication process is etching, which is a key step. Etching is about removing specific areas of material from the silicon wafer to create a pattern. This pattern is crucial for forming the intricate circuits of a chip. There are two main types of etching: dry and anisotropic. Dry etching uses gases to remove material, and then it is anisotropic because it etches in a specific direction, allowing for a creation of very precise patterns. Precision is vital in etching because we need to create various layers on the chip with tightly controlled dimensions and depths. Each layer serves a different function in the semiconductor's final structure. To achieve this precision, manufacturers use specialized equipment. The Lam Research Etcher is one such piece of equipment designed for precise etching. Another piece of equipment is the plasma etcher. It uses plasma to remove materials in a controlled way. And lastly, a wet bench is used for wet benching, which involves liquid chemicals to etch the material as opposed to just using gas. Each piece of equipment plays a specific role in ensuring that the dimensions and patterns etched to a wafer are exact, as it will help determine the reliability and performance of the final product. The next step in line is deposition. Deposition is a step where materials are layered onto the silicon wafer. These materials can be conductive, insulative, or sometimes both, and they are added to create the various parts of a semiconductor circuit. There are two main methods of deposition: chemical vapor deposition, CVD, and physical vapor deposition, PVD. In chemical vapor deposition, gases react on the wafer's surface to form a solid material. In physical vapor deposition, physical processes such as heating are used to deposit the materials instead. For these deposition processes, specialized equipment are used, such as a sputtering system, which is an example of a piece of equipment for PVD method, where atoms are ejected from a solid target material and then deposited onto the wafer. An epitaxial reactor is used for a specific type of CVD process called epitaxy, where the deposit layer has an ordered crystalline structure. Each piece of equipment helps build the semiconductor by adding the necessary layers to create the circuits that will eventually power electronic devices. The final step I'll go over in the semiconductor fabrication process is chemical mechanical planarization, or CMP for short. CMP is used to flatten and smooth the surface of the silicon wafer. It combines both chemical and mechanical techniques to polish the wafer. Why do we need CMP? Because we need the wafer surface to be perfectly flat, smooth, and uniform. This is essential for all the steps in semiconductor fabrication, where the layers of materials are built up on the wafer. The flat surface ensures that these layers are applied evenly and that the patterns created are precise. The integration of CMP in the manufacturing process allows for high-level precision and patterning needed in modern semiconductors. As for the equipment used to enable CMP is the CMP polisher, which physically grinds down the surface of the wafer while also applying a chemical slurry that helps polish it. Another piece of equipment is the slurry dispenser, which supplies the polishing mixture used during the CMP process. The CMP process is one of the most important is because it interacts with every other step of the process and ensures reliability of the layers built on the wafers themselves for the semiconductors. After the semiconductor fabrication process in the front end of things, we go to the back end of things. After the packaging occurs, it comes in inspection and testing. In the process of making semiconductors, inspection and testing are crucial to make sure everything works correctly. Quality control is all about checking for defects and performance issues early in the manufacturing process. This helps catch any problems before they become bigger and more costly to fix. At the end of things, there's also a failure analysis, which is used when something goes wrong. It involves looking at the semiconductors closely, often with visual inspection, to see where the issue might be. Electrical testing checks that the may be used as well, and they check that the semiconductor conducts electricity correctly. And then materials characterization can be used to make sure that the materials used have the correct properties needed. The reliability of the semiconductors can also be tested by putting them through stress tests, which simulate the conditions that they'll face in the real world. This also helps predict how long they'll last and how they will perform over time. And to do all these tests, specific type of equipment is used. For example, focused ion beam, aka FIB, can be used to physically look at the semiconductor at a very high resolution to find defects. And then on the electrical testing side of things, an oscilloscope can be used to measure electrical signals to ensure they are at the correct level. And by making sure each semiconductor passes these tests, manufacturers can be confident that their products are reliable and ready for use in all different sorts of electronic devices. While semiconductor components need to pass inspection and testing for quality and reliability, if you get more into advanced semiconductors such as interposer fabrication, they also have to go through inspection and testing. And so imposers are thin layers of materials such as silicon, glass, or organic substances that are placed between the chip and substrate in a semiconductor device. They play a crucial role in connecting different semiconductor dies within a package and can support complex multi-layer structures. The fabrication of interposers involves a process similar to semiconductor manufacturing, where precision is key. These interposers often contain features like through silicon vias, aka TSVs, and redistribution layers, aka RDLs. TSVs are vertical electrical connections that go through the silicon wafer, which allow for 3D integration of chips, and RDLs are wiring layers that redistribute the connections from the dies to different locations on the interposer for better connectivity. Advanced semiconductors rely on interposers to manage heat, power, and signal transmission more effectively, especially in 3D chip architectures where components are stacked vertically. And the equipment used in interposer fabrication can include a CMP polisher for smoothing the interposer surface and a slurry dispenser for the chemical-mechanical planarization process. And understanding these roles of interposer fabrication is important because they contribute to the performance and functionality of these upcoming modern complex semiconductor devices that utilize advanced semiconductors. Here's the glossary. Here are the references.